So the first thing I noticed is that I forgot the word websites after the word scalable. It just didn't scale across the screen, evidently. So what I'm going to do is kind of give you guys just kind of a 10,000-foot overview of scaling techniques. You know, if you have a website, things you might want to do if you encounter certain problems. So how many people have done HTML before? Okay, good. How many people have done like server-side programming like PHP or Python or Java or, okay, awesome. So first thing I'm going to do is I'm just going to give you guys a quick overview of what the stack is. So the stack usually consists of a server operating system, a web server platform, a programming language, and some sort of data store. And just underneath I put a couple examples of what each one could be. So Linux, macOS, Unix, Windows, Apache, IIS, Nginx, LightHTTP, Tornado. Tornado is actually an interesting one. It's actually a library in Python that you just put some code into your Python script and say start it. Starts up the web server right there in your code. And then what do we got? We got PHP, Python, Ruby, Java, ASP, JSP, things you guys all know. And then data stores. So I've broken these onto two lines. Like most people are familiar with relational systems like MySQL, Postgres, Oracle. And then there's this new kind of breed of databases coming out called, they kind of group them into this category called NoSQL. What they are is they're key value stores. So some examples of that are MongoDB, CouchDB, and something we're using at Digg, which is Cassandra. I'll go into a little more detail on some of these things shortly. What is Digg? Digg is Linux and Apache. We use PHP, Python, and Java, and then MySQL and Cassandra. So that's kind of that's not everything, but that's kind of some of the main components. So what we got here is, I don't have a pointer. So this is kind of a typical, so what this would be is like 4 machines. So you'd have like 4 machines, a web server, a key value store server, a Memcache server, and a MySQL server. It's actually possible to run all of this on one machine, but in practice, we don't, just because what we want to do is we want to scale these things out, and if we need to add more MySQL load, we'll just add more MySQL machines and put them into the pools. So what happens for Apache is inside of Apache there's modules, and so mod PHP, and then inside of PHP there's shared objects that perform functionality inside of it to actually communicate to these other services. So there's like there's a MySQL shared object, a Memcache shared object, a Mongo shared object. And those are actually inside of PHP. Okay, what else? These aren't technically part of the stack, as people usually call it, but these are kind of integral components. Usually there's a load balancer and some sort of caching mechanism. So what the load balancer does is it sits in front of your web servers and it balances all of the requests that come in across your servers that you put into the pool. So what I'm trying to show here is that there's 4 requests for the read request coming in, but we're only actually sending 1 request to the web servers. So that's conceptually what the load balancer does. It also can do caching. So if the load balancer gets a request back or a response back from web server 1 for the read request, it can actually cache that response on the load balancer, and then any subsequent requests that request it will just be served directly out of the load balancer. And then caching. Oh, and some examples of the load balancers are Barracuda. There's Barracuda projects. Cisco makes stuff. Coyote makes stuff. There's lots of stuff. Caching. We and pretty much everybody else that makes big websites use Memcache as a kind of a layer between your web servers and your data stores. So what happens is your web server, let's say it needs a user. It needs to access a user. What it will do first is it will check and see if it's in cache. If it's not in cache, then it will go to the data store, fetch it via SQL or key value store or however you're pulling it out, and then put it back in Memcache and then serve that back out. Memcache is basically, it's shared memory across all of your web servers. So web server 1 can put something into Memcache, and then web server 500 down the line can access it back out of Memcache. So that's kind of what Memcache does. Here's an example of Memcache. This is kind of what I just explained. So, so we're looking for the user to 11. We're checking to see if it's in Memcache. If it's not found, actually select it out, put it in Memcache on the way back, and then we have the object here. All right, so I'm going to go through four kind of major sections. You can see the other ones grayed out here. They'll light up as we go along. But kind of the first challenge is sometimes you are just getting so many requests that you cannot possibly actually serve all of those requests out. Digg does somewhere in the neighborhood of 15,000 requests a second, average-ish. We peak out 2 times that. I've seen us as high as 27,000 requests a second. These definitely aren't peaks, but these are numbers I've seen. And there's no way our web servers, if we didn't have some sort of proxy on the front of it, some sort of load balancer or proxy, there's no way our machines that we have in the pool could handle that many connections. Okay, so a couple ways to mitigate too many requests. I already kind of talked about caching proxies or load balancers. So proxies aren't just a thing that kids can go onto at school to get around the firewall to let them look at MySpace. Caching proxies are what I was talking about earlier about many requests come in for the red object. It sends one request down to the web server, gets a response back, and actually caches it at that level, and then can serve it back out. So that's actually the server side. The client side, what you can do is on objects you send back, on responses you send back from the web server, you can actually say, cache control, you can say it expires at this time, when it was last modified. Most modern web browsers are smart enough to actually look at these things, and if an image hasn't changed on your website, it will just pull it out of the cache on your local computer. So adding these headers can help a lot. Okay, minimize the number of requests. This is it's pretty much universal mantra that the one best way to speed up your web page, perceived speed to your client, is to reduce the number of requests that your page makes. So for example, you load a web page up and you load 10 images, 2 JavaScripts, a CSS file. You make a call out to Google Analytics. Each one of those is one request. And what you want to do is you want to minimize the number of those that you make. AJAX are also requests. So less AJAX, the better. And it's pretty much universally, so I think Yahoo is the one that did the initial study, and they looked at how long people would stay on web pages, and they found when they took the number of requests down, people would stay on the pages longer, they would get more traffic, good stuff. So MXHR, this is something that one of our engineers at Digg came up with. Actually, I think there was 2 of them. This is actually the blog post that talks about it. He goes into a lot of detail. I also have all these slides and links, and I'll give you guys a website at the end. So if you guys don't want to write, you don't have to. So what you can do is you can take all of these requests. Let's say you need an image, and you need a JavaScript, and you need a CSS, and you need all these various resources. What you can actually do is multi-part encode all of that content and send it in one request. So what this is doing is it's saying, okay, so these are the borders on the multi-part, and it's saying, okay, this is an image, this is some text, and this is some CSS. And then you have JavaScript on the front end that actually will look at these responses that come back, and it will go through and it will parse out the multi-part pieces and then perform some action on your page with them. If you go here, he's got a demo where we show what happens. I think he loads like 500 images or 600 images or something like that. And using the typical image source, blah, 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 like you're used to in HTML. Takes 10 seconds, 12 seconds. Using this technique, if he just like encodes a bunch of images in one response and then handles them, I think he loads it in under a second. So this is kind of in its infancy right now. If you go, like I said, if you go to the blog post, he's got code examples. He's got the library that will let you actually parse the responses. It's kind of cool. Still infancy though. Another way you can do this. So if you can't reduce the number of requests to your servers, send it to somebody else's. So what they have is these things called CDNs, content delivery networks. And you can take static content, images, CSS, JavaScript, videos. And you can push these to external networks that take requests or that take load off of your machines. And they'll take request load off of your machine. So, let's say you load 500 images on the page, and let's say they're all on a CDN. None of those 500 requests come to you. The only request that comes to you is the initial page load. It's kind of cool. The only problem with loading 500 images on a web page is the actual web browser can only request, 4, 5, 6, 10 requests at a time. So it'll do 10, wait for the 10 or it'll wait for one to finish, and then it still takes a long time to make that many requests. So you don't want to request that much stuff anyway. Just really quick. One of the other reasons people use CDNs, especially like for videos, is videos are giant and people don't want to pay bandwidth bills. It's cheaper to pay the CDN than it usually is to, have the load to actually, like imagine you have like a small website and you only have a certain amount of bandwidth, and you would pay on demand with the CDN. You don't pay, you just don't have like a flat fee. Okay, kind of the last ditch effort. Add more web servers. If your entire scaling technique for requests is to add more web servers, you're in trouble. The only real, you're just not going to get that much more. So your capacity is fairly linear when you do this. In general, it's not the best way to go. And you can tune existing web servers. So Apache, I think by default, don't quote me on this, I think Apache, when it comes compiled for you, can serve a maximum of 250 responses at a time. You can recompile it to do more. You can, as many as you want, but I think 256 is the default. So the default for the max client. So what you can do is you can increase the number of max clients that a web server can respond to, but you can only do that if the web server has enough resources, enough RAM, enough CPU, enough bandwidth on the network. Yeah. Okay, so that was some of the techniques to handle connection load. So web server load. Sometimes you just have so much stuff. You're just doing so much work on the actual boxes once the request gets accepted that it just takes a long time to complete. So there's generally going to be like two ways to approach it. There's going to be code changes and then architecture changes. So optimize your code and how you use the code. So caching code. So I talked about the load balancer already, and I talked about Memcache already, but there's also this thing, so PHP in particular has this thing called APC. What it is it's an opcode level cache. So when the PHP script is interpreted, it will take the generated opcodes from that PHP script, stuff it into APC, and keep that on the server. So subsequent requests, they don't actually have to go through the whole compile state on a PHP script. You get pretty good performance increases if you just throw APC on your machines. You can also cache templates. This really only applies to if you're using a templating system that isn't in the native language. So PHP itself is a templating system, but people use stuff like Smarty. There's a whole bunch of them. But Smarty in particular, which is one of the template systems we use at Digg. It uses a kind of meta pseudo-ish HTML that does some variable replacement. And then when the page is requested, it compiles that PHP or that Smarty template into a PHP file. So what you can do is you can actually cache those generated PHP files on the server. So it's a little bit of a speed up, not monumental, but it helps. Caching data outputs. So let's say you have some sort of calculation you do on your web server, and it just takes a long, long time. Like, let's say you have to sum up, the total GPA of, 1 million students or something like that. Something. What you can do is do that, and then cache it in Memcache, and then subsequent requests you only have to go to Memcache instead of doing that whole calculation. That's kind of an example of caching your outputs. The process itself isn't that complex, and getting the data isn't that complex, but it just takes time to go through the loop. So cache the output. And then you want to use, so all of these caching mechanisms have expire times on them. And expire times are it's kind of an art form. You kind of want to think about how long you're okay with your data being stale for. Caching can range anywhere from a couple seconds to days or hours. And then kind of the last thing, and I put it last for a reason, is you want to profile your code. In PHP, there's two products that I know of at least, which are Xdebug and XHprof. XHprof is it's a Facebook project. Basically what happens is you run your script, and it looks at every single request and every single function request and every single call, every single piece of data that's accessed, and it creates a profile of what happened during your script. And it dumps a file onto your system, and then you can load it up with a profile inspector. And then you can look and see, this function ran 5,000 times, this function ran 50 million times, this function. So you can go through and find out which functions are being called the most, which processes you're spending the most time in. And then it's a kind of a good way to go and target where you want to go and try to optimize the actual code and do some of these other things like caching the outputs of the processes and stuff like that. What else do we got? Okay. Oh, so scale the architecture. So generally there's two ways you scale. You either scale up or you scale out. So scaling up refers to more powerful hardware. I mean, that's really what it comes down to. So if your web server is overloaded, get a faster processor, get more RAM, put more network speed on it, put a bigger hard disk in it, whatever is bogging you down, more. So that's what scaling up does. Generally, not the best approach, once again. It really only makes sense if the pace of hardware innovation is exceeding your actual growth. An example of this, and I'll actually talk about this when we get to databases, is 37 Signals, the guys that do the Ruby on Rails and Basecamp and all those products. Their approach to scaling their write database is they just keep getting faster hard disks and more RAM, and they put as much into it as they can. I think he said he switched to like SSD drives for their database. And Ben, do you know how much RAM they said they put in that machine? Yeah, they just put ridiculous amounts of RAM into these boxes. They put ridiculous amounts of storage, and they just get the fastest whatever they can. And they say it works for them. Kind of cool. And it's easy to do. That's the other thing. Scaling out is harder. So generally what you have is you have a load balancer, you have many servers. That's kind of that diagram I drew in the front where you have a load balancer and you have n web servers sitting behind it. The only problem with this is you have to take some care to make sure that you have to make sure that like your code that you're running on, that you're actually serving out doesn't require a specific machine to actually run. Some examples of this are like sessions. So I think by default, most PHP installs, they load all of their session data into onto the file system in like /temp. That doesn't work when you're hitting multiple machines. It's, you know, you hit server 1, you load your session there, you go to server 2, your session's no longer there. So like one of the approaches you can do to this is you can actually change it so the sessions are actually stored in Memcache, which we already talked about. So you just have to make a lot of changes like that to make sure you don't require machine affinity. I don't know if they still do this, but as of about 2 years ago, Flickr actually just stored your complete session in a cookie on your machine. So they didn't have to worry about storing sessions on the server. Your session actually was on your machine and it followed you around and they did whatever they needed to with it when you sent the cookie to them. It's pretty cool. Oh, and you have to be able to scale out if you want to run in multiple data centers. If you have one machine, you can't put it physically in 2 places. It's kind of that one's kind of a simple one. Data store load. Okay, so you can't read or write data fast enough. Usually the problem, well, it's not usually the problem, but it's going to be one of the two. So first thing you can do, so I'm going to go through read access first. So what you can do is you can make code changes. And so all of these, it's either code changes or architecture changes. So code changes, cache the data. So we already talked about Memcache. Oh, that's great, messed up that slide. So Memcache, what you do is as you get results back from your database queries, you actually just stuff those into Memcache, and then subsequent requests, you go to Memcache for them instead of the database. This can take load off of your databases, makes for happy database administrators. And then, so that's the URL for where to get Memcache and find out more about it. Caching strategies. So you can cache on access, which is what I've been describing up to this point. You decide you need a piece of information. You find out if it's in Memcache. It's not. You go to MySQL. You get it from MySQL. You put it in Memcache, and then you stuff it back out to the user. So that's like caching on access of the information. You can also prime your caches. We do this for some stuff at Digg. If you know you're going to need certain pieces of information in high volume, you can actually run jobs in the background that go through and they find all of the pieces of data that you're going to need, and they just stuff them in the cache before anybody ever requests them. So when they actually make that initial request, it's there. So I'm going to jump out here for a minute, and I'm just going to show you a test of MySQL versus Memcache. So this is all running on my local machine, so you can take that for what it's worth. Oh, come on. There we go. All right. Where's my... So what I did is before we started, I went and I actually populated Memcache with 100,000 records. So the Memcache queue is completely primed right now. So PHP, MySQL.php. So what I'm doing here is I'm grabbing 100,000 records from a MySQL database. Blah, 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 blah. And all I'm doing is grabbing them and doing nothing else. I'm not operating on them or anything. Then I have some timing in there. So okay, so what it did is it did 100,000 records, and it took just over 12 seconds to grab all 100,000, and no invalid requests. So that's good. So here's the exact same process, but getting it from Memcache. Still takes a little while. Half the time. And this is on just this machine. So it's, a couple gigs of RAM and a moderately okay processor. But when you put these on like big machines and lots of servers with lots of really fast RAM and fast processors, and it's substantially better than this on real machines. But this is the kind of stuff you can expect. And this is actually, the query I was doing here, I was actually doing primary key lookups. So I was saying selects from users where ID is 1, ID is 2, ID is 3. Those requests are really fast in MySQL. If I was looking at by like username, these requests would be even, this one would be way slower. Even if I had an index on it, it would be slower. So Memcache is faster. That's the take home here. Let's go back in the presentation. Okay, so that's what we just did. We just did the test of fetching 100,000 users from MySQL and Memcache. So what else can you do in code? You can optimize your queries. So we use MySQL. So the command in MySQL to look at how your query is interpreted by the server, it's called explain. So you just put explain in front of a query, and it actually tells you the process it goes through on how it joins tables, which indexes it uses, how it's sorting, if it's sorting it in memory, if it's sorting it on disk. Basically, you don't want to ever have to write to disk in MySQL. That's where you get your real slowdowns. So you explain, and you can kind of get some information about what's going on, and that kind of gives you a clue on some other things you can do to help with your queries. Okay, so let's say you didn't explain, and it said it's doing a text-based comparison of your key. Well, that's not very efficient. What you want to do is you want to do an index. You want to look up on an index. So you can add indexes to columns. Indexes take space on the hard drive, though, so you don't want to go completely crazy with adding indexes to your tables. The interesting thing about indexes, MySQL can only use one index per table. You can have multiple indexes, but when you run a query, you can only use one of them. So typically what you'll see is you'll see an index on the ID, you'll see an index, like let's say you have a user table. You'll have an index on the ID, you'll have an index on the name, then you'll have a joint key on user and like date registered, for example. So if you want to get all users registered before a certain date or after a certain date or whatever. So you'll actually create like multiple indexes because you know you can only use one of them. That's kind of a MySQL specialty. Okay, so sometimes many single simple queries are better than one complex one that accomplishes the same thing. We do this a lot at Digg. Not this exact query, but so let's say you have this particular example. This query winds up being faster than this, but imagine you have a really complex query here that does a whole bunch of joins and a whole bunch of group bys and aggregate stuff, and it counts some results. And if you can reduce that down to where you're looking for a slice of that data, and then you do it multiple times, usually this query will wind up being faster even if you iterate over it on those complex type queries. The reason being, like especially when you do a join, it has to join the tables together, and then if the size of that join exceeds your available RAM, it writes to disk. Once you write to disk, you're in trouble. You want to do everything in RAM on MySQL. So doing small things like this, like when you say user ID is 1, you basically chop the table down to like one row before you do the join. That's kind of the idea here. Instead of doing, a million times a million, you do 1 times a million. So that's kind of that's what we're talking about here. Oh wait, hold on. I had some notes here. Oh, the other benefit of doing this is you're basically set up to add caching right here. So if you select out, you get one row back here. You just take the result of this and stuff it in cache right after. Whereas like if you do it here, you'd have to write a loop, iterate through all the results, stuff them into cache that way. So the caching is not a huge win, but you're kind of set up for it already. All right, so scaling out the architecture for read load. There's generally I'm going to talk about 4 approaches. So you can scale out read slaves, which just means add more of them. You can vertically partition your tables. You can horizontally partition your tables, and then you can do data denormalization. That will probably make whoever your database teacher is cringe, but you can do it. So scaling out read slaves. So this is kind of what a typical database system it isn't what our databases at Digg look like, but usually you have like one server that handles all the write traffic. And then you have multiple servers that get replicated all of the data to them. So what happens is a query comes in here, it gets written to the write master, and then it flows into all of these other machines. And then your code that actually accesses your data, it talks directly to these machines. It never talks to this one when it does a read. So what you can do is you can just add more of these in and tell your code that there's more of them, and it will distribute the load across all of your read slaves. So that's what I mean by scaling out your read slaves. What else? So we talked about load balancers to balance traffic across your web servers. Some people actually will use a load balancer. So imagine you have like a PHP script here. They'll actually put a load balancer between PHP and between MySQL, and just let the load balancer take care of choosing which server to send the query to. Okay, vertical partitioning. This is a wacky one, but it's interesting. So imagine you have a table users, and that's the schema. Not necessarily a very great schema, but that's the schema nonetheless. So you got an ID, a username, a password, secret question, secret answer. You got their favorite color. You got whether they're active, and you have whatever their website is, or their list of websites. So what vertical partitioning is, come on, is it's this. You take that table, you split it into 2. You put your most accessed stuff into the main table, and then you create a table you join against for the additional data. So, and then you key it on the user ID. So secret question, secret answer, those aren't ever going to be used except for when somebody loses their password. So stuff it in that other table. You don't need that most of the time. Favorite color, website, same thing. So you put, and these are the bigger pieces of data. 100 characters, 100 characters, unbounded, well, bounded, but large. So the bigger data is in the table that you don't have to access as much. What this allows you to do is, let's say I have a piece of code and I need to join I think at Digg we have a table that holds all the stories. Let's say I need to get the username of the person that submitted the story. All I have to do is join against this table and get the username. Where this is a win is what I was talking about earlier about how you don't want to go exceed RAM. These tables are physically smaller in actual like storage space and size. So when you join on these, you're more likely to keep it in RAM. That's kind of the theory here. We did this on some tables at Digg. We saw some benefits. We didn't see giant benefits, but we saw some. All right, so what else we got? We got horizontal partitioning. So I've used the technical term. A lot of people you'll hear refer to this as sharding. So what you do, and I've done a really stupid example here where So all the data here, 0, 1, 2, 3, 4, 5, blah, 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 is on all of these original machines. When you shard the data, you put some subset of it on one group of servers, some subset of it on a completely different group of servers. So in my scheme here, I put all the evens on this group and all the odds on this group. What this lets me do is it lets me just add more read capacity that way. It also lets me add more write capacity. So let's say I have an even numbered insert I want to do. I have to go to that one. If I have an odd numbered insert, I have to go to that one. So the real challenge here, though, is when you do this, you don't want to do even odd. You want to do some sort of hashing function that lets you keep adding machine. Like, you don't want to have to add 2, or you don't want to have to add 10 or add 100. You want to be able to grow as your business or as your website grows. So what you need is some sort of consistent hashing consistent hashing function that as you add more machines in, it can start distributing that traffic to more machines. So I'm not going to go in too much into it because I don't really even know what it is that well, but there's some circular hashing that you can do where you can, basically you draw a circle, you put all your available web servers as points on the circle, and then you map your piece of data to a spot on the circle, and then the closest web server is the one you send it to. Like I said, I don't really get it. Like, we don't. Well, I can't say we don't do this actually, because we tried this thing called IDDB, and we created a product called IDDB we were using internally, and it was basically this. It's a pain to do this. If you can avoid it, don't do it. Just don't do it. Well, if you have a good way of doing it, it works great, but it's hard to do. So last thing, data denormalization. So here's what it is. Basically what you do is you replicate data into all the tables that need it. So, for example, like in Digg, the username doesn't change that often. Like, you register for a username, and I think the only way you can change a username is by emailing somebody and asking them to do it. So we actually will replicate pieces of data like that out to multiple tables. So the users table will have it, the stories table will have it, the comments table will have it. Oh, great, my time. So one of the real wins is you don't have to join as much. So like when I was saying earlier, you can join and it stays in memory. If you don't have to join, even better. So if I want to get the username of somebody who made a comment, all I have to do is look at the comments table. I don't actually have to go join it against users. Drawbacks. When you want to update that piece of information, all of a sudden, like in this example, you have to update it in 3 spots instead of 1. So like I said, it's best used on rarely changing data. Let's see. Oh, you also can't do this. Well, it's good to do this because you can't join if you have data. I'll talk about this in a minute, but you can actually take data and put certain types of data on certain machines. So, you might have users on one set of machines. You might have stories on another set of machines. You might have comments on another set of machines. You can't join across the machines. Well, there's probably products that let you do it, but not easily. So that's another reason why this is great. Okay, so scale the system architecture. So we just talked about all the stuff we can do in code. Yes, so we can scale the architecture for write traffic now. So we were talking about read before, now we're on write. So query-specific server pools. This is what I was just talking about how you, well, I'll just go through these real quick. Query server-specific pools, you can scale out your writable servers, and you can do horizontal partitioning on this stuff. And then our DBA at Digg, he posted this nice long post about exactly how we have Digg architected, database-wise, and that's the URL for that. He talks about all of this stuff. And he goes into substantial depth. So query-specific server pools. What you do is that structure we talked about along the way, you just take it and you replicate it out. You send certain queries to this set. You send certain other queries to that set. So for example, digs is a very high, we get lots of digs. So we want to put them on their own write machine. Users and items, we don't get those as often. So we put those together on a different machine. We actually read these ones more than we read these ones. So what you would do is you would actually add more read servers over here. You would have less read servers over here. So you can actually allocate your machines to your traffic and to where you need the extra power. So this is what I mean by query-specific server pools. You can actually create silos of where your data goes. What else? Come on. Okay, scale out the writable servers. This is a pain. This is, I put a lightning bolt here because it's magic to me. So Digg, you get a Digg, and you send it to your write machine, and it magically goes to two write masters. And then it gets replicated out from one, or it gets replicated out from both. But then the process to sync these two machines up so they don't have colliding keys is magic. So syncing them up so you can do concurrent writes to both of them, that's the hard part. If you want this for a kind of a failover scenario where you have, let's say you write stuff here, you write stuff here, or you broadcast down, and what they do is they just sync across, and they make sure that each one, actually, in that scenario, what you do is you get rid of this write. It writes to this machine, and then it just replicates over to here. You have a hot swap machine. So if this database goes down, you just put this one in, and it's up to date. But that doesn't help with your write traffic. That just helps with redundant, or it helps with, something breaks. So generally, this is hard. Horizontal partitioning. This is the same thing we talked about earlier. So this is the exact same picture as we talked about earlier. So I talked about sharding and creating these different groups for the odds and the evens. So this scenario also, it helps with your write load as well, because you can send odd writes here and even writes here. Same caveats with consistent hashing. This is also a pain, like I said before. So what else? Key value stores. So there's a whole bunch of products. There's MongoDB, there's Voldemort, there is CouchDB, and there is the product we use at Digg, or we've just started using it, and we're putting some significant resources towards it. It's called Cassandra. They're all key value stores. So the benefit, usually they're faster. This is the big one right here. They're suited to horizontal scaling. Actually, these are both big ones. Suited to horizontal scaling, and they're incredibly redundant. So what happens is these things work in a big array, once again, but they have the logic actually baked into them, so we don't have to do it. So what you do is you broadcast a write into the system. You can write to any one of the machines in the pool, and then it figures out which machine it should go to, passes it to that one, and then usually, I'm just gonna draw here. So you have machines sitting on a ring like this, and let's say you send your write to here. It says, oh wait, this write actually needs to go to here. And then you have, well, let's say you have three. You have three servers in succession on the ring that are all responsible for handling that piece of data. So this right here goes to here, here, and here. So number of servers you have to write to, 3. Because we can add many, many servers and any server can handle any write, it's faster. Also, because we're writing to 3 machines, we're also redundant now. There's also read-write trade-offs. So we can say we want our reads to be slower, or we can say we want our writes to be slower. I can talk about that later after, because we're running out of time. Drawbacks, ad hoc queries are really, 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 really hard. So you can't say, I want all users that were registered after a certain time period, and their name starts with an A. You can't do it. It's just, you can do it, it's just really, 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 really hard. So these are some papers on key value stores. There was a big get-together in San Francisco. It was called the NoSQL Debrief. They did presentations, like 20-minute presentations. They videotaped all of them, so you can go read up on or listen on any one of these key value stores you want to listen to about. And our lead architecture on our engineering team created a blog post called WTF is a super column Cassandra data model. This is our kind of our Digg. So when we were going into Cassandra, he found that nobody had good examples, so he just created this. And actually, this is kind of a example of what data model in Cassandra looks like. Nothing really important. I don't. How much time do we have left? We're almost out. So basically what this means is you want to take as much stuff as you do in serial, and you want to parallelize it. So you can use things like messaging queues, asynchronous messaging queues. You can use cron jobs in the background that do stuff. You can use offline MapReduce jobs like Hadoop. So here's an example of what we do with, or what we can do with Gearman. So instead of saying fetch all users, do something, fetch all items, do something, what you can actually do is you can tell Gearman to launch both processes at the top and then continue on in your code. And when you actually need the data, check to see if it's there. So what you would do is you would write the results of these Gearman jobs into Memcache. And then when you actually need them, you check to see if they're ready for you. So you can do all of your data access asynchronously. It's pretty cool. Any questions, comments, flames? Nothing? Yeah. Yeah, I'll definitely hang out for a while and answer all the questions you guys need. Go ahead.
Say you want to store something in Memcache. Does Memcache already check to see if it's already there?
So there's different operations. There is a just push it into Memcache. There is a check to see if it's there and replace it. So basically you can do any of these operations. But generally, if you do a set on Memcache, you overwrite the expire time that's currently there, and you just put it in the same spot. Anything else? Anybody? All right. Thank you very much. So the PDF of this it's on my website. So go sfrench.com. There's a link on the top that says talks, and it's got links, and it's got a link to the PDF of all this.